Today's episode is sponsored in part by Palo Alto Networks and its Prisma SASE, where AI-powered innovation takes center stage. Watch the new Palo Alto Networks virtual event on demand to hear how the latest innovations in SASE can help your organization. See how ZTNA 2.0, Cloud Secure Web Gateway, and SD-WAN deliver exceptional security and ROI. Watch on demand at paloaltonetworks.com/engage/SASE-signature-moment.
Welcome to Heavy Networking, part of the Packet Pushers network, a fine technical podcast for IT engineers. If you've ever wondered why Ethernet frames don't have a time to live field, how to automatically rate limit someone's port when they visit an adult site at work, or why IPv6 isn't backwards compatible with IPv4, you found your tribe. I'm Ethan Banks along with Drew Conray Murray, and you can connect with us on LinkedIn or chat with us in the Packet Pushers community Slack, which you can join at packetpushers.net/community. Our guest today is Russ White, a somewhat regular guest. If you don't know Russ, he has authored many books, I think 13, on networking technology, worked inside the industry at a variety of vendors you've very definitely heard of, driven the creation of at least one certification, and served in the IETF and IAB in many different roles. I could go on, I really could, but in the interest of time, I will not embarrass Russ further. On today's episode, Russ chats with us about a grab bag of topics we wanted to get Russ's opinion on. This might even have to be a two-parter because we have too many topics to discuss for the time allotted, so let's jump in and see how this goes. Well, before we do, if you are listening to this episode during the last week of May, I will be at AutoCon 1 in Amsterdam. That is a network automation forum event. If you're around, come by and say hello. And if this is the first you're hearing of it, networkautomation.forum, check out AutoCon 1 that is happening in Amsterdam, and come on by. Would love to say hi and make your acquaintance. Russ, it's been a while, man. Welcome back to Heavy Networking.
I know. I'm always trying to get you on the hedge too. But by AutoCon, if I could actually get to Amsterdam, my face might be a little bit less red from all that introductory material.
Well, Russ, we've got a grab bag of topics that we wanted to chat about today. One of these was a topic in the Packet Pushers community Slack group that you engaged with. Someone had asked a question, kind of a very practical question about Ethernet adapters, and how does an Ethernet adapter know when link is lost, which got interesting. That thread went on a kind of longer than I thought it would, and I thought maybe you could shed some light on this very practical question.
Wow. Okay, sure. So Ethernet chipsets, PHY chips, have two different ways they can figure out that the link is lost. And actually, it's probably more than two. Depends on the version of Ethernet. So all Ethernet types can just figure out that the carrier is gone, loss of carrier. Flat out, I have no more signal. Contrary to what we might believe, and I was just discussing this the other day, interestingly, with somebody talking about energy awareness in networking. And they were saying, oh, but everybody thinks that if I just transmit less, I'll use less energy. That's really not the way things work. For those of you out there who think that, that's wrong. No, don't do that. The carrier is always up. You're always using power to send carrier. You only modulate on the carrier or you don't. That's the only difference in the way things work. So if the carrier goes down, there's been a physical break. Well, that's really cool if the carrier's gone down. But what if the carrier hasn't gone down? Well, some versions of Ethernet, and I don't remember them off the top of my head, I just know that I've worked on such things, have the ability to send essentially like a BFD, a very fast packet, a very fast hello packet at layer 2 that they send.
Not BFD. You're just using that as an analogy. You're talking about bidirectional forwarding detection.
Yes, not BFD.
Okay, yeah.
Correct. Yes. Maintenance and what's it called, Ethan? Maintenance and something. something. Anyway, yeah. There are versions of Ethernet that have maintenance on them that can send very fast hellos at the layer 2 or at the data link layer. And then from there, they can figure out if the link is down or not. Now, where things get tricky with Ethernet is when you get into switching. When you have a switch in the middle, you don't get loss of carrier because the link itself is between the switch and the interface. It's not end-to-end to the destination host, even within the same broadcast domain. So there you get into things like BFD. And interesting history for you, there used to be a thing called MARP.
Oh, I don't remember what that is, but that acronym rings a bell.
Yeah, there used to be a thing called MARP, which we were trying to do which was essentially when the switch detects link down, it does an inverse ARP, taking the ARP cache or clearing the ARP cache for that MAC address from all connected devices. So if I'm point-to-point connected with an individual device and I see link go down for that particular device, I could, as a switch, notify everybody who's connected to me. I don't know if you actually have this in your cache or not, but please take it out if you do, because they're gone.
Mm-hmm.
That MAC address is no longer reachable. And that was something called MARP, which didn't really take off because, of course, it had to be put in the switch hardware and everything else. And you know how messy that gets. BFD took off instead because it was all software and initial implementations.
So you ended up talking about a couple different scenarios. One scenario was between an interface and a switch. And then a different scenario is, well, what if we're trying to detect Ethernet link between an endpoint and another endpoint, but there's a switch in the middle, which is really a different thing.
Yes.
So let's roll it back a second. If we go Ethernet to switch, and I lose carrier, what does that mean? Like if it's copper, I've lost electrical signal. There's nothing on the copper anymore. And so I know because I've got no signal there, no electricity flowing across the contacts, link is down.
Yes. Or optical. I have no laser. I have no physical, like there's no photons, there's no electrons flowing, whichever one it is, depending on the link type. That would be loss of carrier. I'm gone. I have nothing to transmit on. I mean, I can transmit, but nobody's going to be able to talk to me because
going back to your original point, even if there's nothing being said on the link, electricity or photons are going to be flowing. There's going to be something there. And again, to reiterate your first point, if the carrier, the only difference is going to be that the carrier wave is going to change because it's actually transmitting data.
Correct. That's correct. Yeah. Even with like differential Manchester encoding, which is what a lot of early Ethernet used, you still have a signal. Now, in the modem world, you didn't used to have this, right? Because you only transmit audibly when you're sending data. So what you had a separate signal that was sent on a different wire, basically a hardware hello, which was essentially like a secondary carrier. And that as long as that carrier was alive, you assumed that all of your other signal pairs were good and you could continue sending.
So how does PoE factor into any of this? Kind of a different thing, but sort of related?
Yeah. No, totally different pair of wires. Not at all. You can have PoE and lose carrier.
And
you can have carrier and lose PoE. Yeah, it's a completely different set of wires.
And PoE is only going to come across that line if it's called for by the endpoint saying, hey, or is it? No, PoE would be sent across because it can't ask for it if it doesn't have power. Hang on, chicken or the egg.
True. Yeah, exactly. Yeah. So no, I mean, but the thing with PoE is, I mean, it's so important that PoE is direct current rather than AC, rather than alternating current, because if it were alternating current, it could actually interfere. It could actually inductively cause near-end crosstalk or far-end crosstalk on the cable pairs, because PoE is very high power compared to the power on the Ethernet segment or on the wire itself. And so if you had AC running on that wire, inductive reactance would get really horrible real fast, and you would end up with all sorts of crosstalk.
Okay, now I want to go back to your signaling discussion where there's a very fast signal down at layer 2 that can happen for some Ethernet. It's not as simple as loss of signal. We're actually doing something kind of like BFD and testing that there's link there. But you're saying that's not between the endpoint and a switch? That's between an endpoint and an endpoint? Or
no, that's on the PHY chip. It's called OAM. And OAM is on the PHY chip itself. It's not. It's point to point. It's
now when that happens, so there's loss of carrier there. What is that adding to the mix? That a simple loss of carrier or detection that there's no carrier there anymore isn't good enough to detect.
Well, sometimes you can be in situations where the PHY chip has carrier, but it's not able to transmit anything for some strange reason. There are hardware failure types where the carrier can be generated, but you still can't send data. So in that case, OAM would actually find that or detect that.
And that sounds like it's a lower level than something like UDLD, on unidirectional link detection, would be sussing out, where you can transmit on one pair, but you can't receive, let's say.
I would call UDLT a form of OAM. There are other forms of OAM that you will find in the world in different versions of Ethernet besides UDLT. I don't know how popular they are. I just know this came up a lot when I was first working on a lot of Ethernet stuff. When we were looking at MARP and we were looking at BFD, there was also a move afoot to get a lot more low-level hello type stuff into Ethernet. I don't really track the 802 standards as well as I should in that realm.
Well, there's another question. I mean, BFD kind of rules the world there, and we tend to think as network engineers very often in terms of layer 3 and doing the detection at that level. How often do we need to actually care what's happening down at the Ethernet layer?
Well, I don't know. Carrier detect still is going to be faster than BFD.
Mm-hmm.
No matter what you do, carrier detect is going to be the fastest. Even if you have OAM like UDLT or something, you're still going to have carrier detect is going to be the absolute fastest way to detect down because it's just physically the signal stops coming.
Yeah.
There's no 3 times a hello. We think of BFD being very fast, but you have to drop 3 BFD packets to declare it down, or 5, or whatever, however you have it configured, whatever the configuration is, 2 or 3 or 5, or just depends on your configuration. In carrier down, it's just down. Like I have no carrier, I'm down.
So here's a follow-up question then. The rest of the router needs to know that that interface is gone so that it can begin its convergence process, update bridging tables, et cetera, anything that needs to get updated. How quickly does the operating system know, well, interface is down, carrier's down, and begin to make those changes? Because there's got to be a path to push that data up the stack.
Yeah, it depends on which part of the operating system. So typically speaking, the PHY chip, so the PHY chip has a hardware interrupt line to the ASIC or to the switching engine, where the forwarding engine, whatever it is switching the packets it's going to have. So every time the PHY chip reads a packet in onto the receiving, it's generating a hardware interrupt directly to some physical piece of hardware through a hardware signal. Like it's not like a software thing. And that tells that chipset to go grab the stuff off the receiving. And of course, it may wait for 5 packets or whatever. That's all, however the forwarding engine or the processor is set up. But in this case, when I see an interface down, when I see my carrier loss, I'm going to send a hardware interrupt telling basically the PHY chip, or telling the PHY chip, telling the forwarding engine or whatever, this is gone. Don't use me anymore. Take everything that you have on my transmit ring off. Like my transmit ring needs to be cleared right now. There's nothing I can send. Now, so when that happens, depending on the programming of things, if, for instance, you're using a next-hop group and you have multiple next-hops via ECMP in the forwarding engine itself, programmed into the forwarding engine itself, the forwarding engine can, as soon as it gets loss of carrier, so we're talking 10 to 20 milliseconds, once it gets that hardware interrupt, it can take that next hop out of the next hop group and start forwarding traffic around, even before the routing protocol starts doing anything or even knows about it, even before the RIB knows about it. The forwarding engine has the ability to just say, oh, I don't know what happened out there at the PHY chip. The PHY chip is telling me this interface is gone. Fine. I'll take it out of my next hop group. Now then the forwarding engine is going to have a way, a back pressure or a callback into the RIB, and the RIB is going to now get next notified of that down. Because what's going to happen is the forwarding engine is going to say, I took it out of the next hop group. I need to tell the RIB, take it out of the next hop group as well. I need that next hop to be gone from the RIB. So now I can tell all the other forwarding engines in this box, if there's more than one, just chassis box or whatever, to stop sending traffic to that interface, to that next hop represented by that interface. It's going to be a group of next hops, of course, not just one.
This is interesting. This is backwards from the way I would have imagined it working, having not dug into this myself. I would have assumed Okay, there's going to be a software notification. It's going to go up to a software layer in the operating system, which will tell the RIB, which will then repopulate the FIB with the new information. But no, it doesn't go like that at all.
No.
That is counterintuitive to me.
And
it's faster
RIB,
though that way.
Oh yes, and then the RIB has a callback into the each routing protocol, saying your next hop that you installed this route for, that next hop is gone. If you have neighbors on that next hop or you have something going on, you need to kill all that and recalculate. So it all comes up from the PHY chip. Now, BFD is a little bit different because, of course, BFD is going to take the logical interface down. So, yeah, it comes from the RIB or the FE level, depending on where BFD is running, rather than from the PHY chip. Yes. So it depends on how the interface down is.
That's the difference, because one's coming from something physical. The BFD would be coming from a software process that's going to inform another software process, and then it's going to trickle down as opposed to being pushed up from the hardware.
Yeah. Now, originally, BFD was supposed to be built into PHY chips, and it never happened, right? But that was the original idea, is that I would have BFD running at the PHY chip, so it would be like carrier detect. It would work the same way as the carrier detect does, or loss of carrier. But that's never really happened. There was the idea of, if I have a chassis box, I could put a BFD processor on each line card. And so everything would come up from the forwarding engine rather than coming down from software. So that's all very, yes, but it is upside down. It was quite interesting the first time I traced that through the code. And I mean, old Cisco iOS, but that's true in every operating system I've ever looked at. That's the way it works. It always comes up from the PHY chip. Hardware interrupt, FE to RIB, RIB to routing protocol. And by the way, this is one of the reasons you get microloops in link state protocols.
Because it takes the routing protocol a little longer to notice and be able to react to what's happening physically.
Yes, and the FE is already forwarding. And if the FE is already forwarding to a different next hop, which is actually a loop, and it's all order of operation. This is all order of operation stuff. So, yeah. And
by microloop, you're talking about, this is sub-second kind of stuff typically.
Yeah, most of the time microloops are 100 to 300 milliseconds, maybe 500 milliseconds. They don't hang out for very long. They're hard to find. They're hard to see. Like, it's very hard to actually, oh, look, there's a microloop. I've tried to slow timers down and make it. Yeah, exactly. I've tried to slow timers down and make it last, but it's really hard to do.
Do you feel like the physical layer has gotten more robust over the years, that we're having fewer issues at this layer?
Oh yeah, definitely. Back when I first started in networking, we were running inverse multiplexers over hardwired, and I don't mean hardwire. I mean 66 blocks punched together, or 100-pin cards with the turn down, with a little turny thing on it that you strip the end of the wire and turn it down type of thing. Those are very unreliable connection types, and so you get a lot of noise on those circuits. And even
you know how to put even more noise on the circuits? Get a tone generator, because you share that 66 block not only with the Ethernet infrastructure, but with the phone infrastructure. And so your phone guy walks in the closet with his tone generator, runs it down all the contacts and blows up the Ethernet. Ask me how I know.
Yeah, we actually used to have Tommy Conrad cards that would blow up when you did that. Literally blew the chip out. You have to replace the card when that happened, or when there was a lightning storm. Either one, they were very very delicate little cards. Poor things.
No, we'd have that happen, and we couldn't figure out what it was for a while. And I had a suspicion that it was our phone guy, because he was working on a cabling project. I sprinted in there, caught him with the tone generator in his hand. I'm like, dude, you can't do that. You're killing the network in here. Everyone's getting knocked off. What's happening? Stop. He's like, oh, sorry, man. And as soon as I told him what was going on, he thought about it. I was like, oh yeah, no, that'd be bad.
Yeah.
The old days.
Let's pause the conversation for a message from sponsor Palo Alto Networks. 2023 is a year when companies are going to need to do more with less. As businesses grapple with economic uncertainty, it's more critical than ever to consolidate fragmented security and networking solutions to reduce operational complexity and costs. Palo Alto Networks has a new virtual event on its Prisma SASE, where AI-powered innovation takes center stage. You can watch this event on demand and see how ZTNA 2.0, Cloud Secure Web Gateways, and SD-WAN deliver exceptional security and ROI. Hear how the latest innovations in SASE can help your organization automate costly and complex IT operations with AI-powered digital experience management, connect and secure branch offices and the hybrid workforce with SD-WAN, ZTNA 2.0, and Cloud Secure Web Gateways, and unlock better ROI through consolidation of point solutions with Prisma SASE. Watch this event on demand at paloaltonetworks.com/engage/SASE-signature-moment. That's paloaltonetworks.com/engage/SASE-signature-moment. And now back to the podcast.
Well, Russ, here's our next topic. And I can tell based on how long it took us to figure out why was an Ethernet adapter no when link is lost. This next question is going to be a doozy. OSPF versus ISIS. Why would I choose one over the other? What are the design requirements that would make it a relevant decision where I actually should be picking OSPF or ISIS?
Oh, my goodness. Well, one is a 4-letter protocol and one has a dash. And I've always taught my children not to use 4-letter protocols. Sorry.
I've been reading this book. I've been reading this one. There's more differences than that.
Who is that?
Doyle, Jeff Doyle.
Doyle. Okay, yeah. Okay, yeah, that's cool.
You were cited in the front. He acknowledges you because I guess you proofread that book apparently.
Yeah, I probably did. Yeah. So anyway, I don't know. I kind of think of the history of OSPF as being unfortunate because they started out with a simpler protocol, but as complex or as hard problems piled up, they ended up with a much more complex protocol than there was a time when OSPF is the simple protocol and ISIS is the complex protocol. And now it's like the opposite. It's totally the opposite. ISIS is the simple protocol. OSPF is the complex protocol. All right. But you have to think back to when we only had type 1s, type 2s, type 3s, and type 4s and type 5s, right? In those days, the complexity level was very similar. Coding the two, however, OSPF was easier to code. Why? Because OSPF uses fixed length fields. So when I grab the OSPF packet from memory, I can just simply overlay a data structure on top of it, and I can read my fields directly.
Okay, you know exactly what's going to be in all those fields. It's been mapped out for you. With ISIS, you've got TLVs, and they can stuff whatever they want in there. Yeah,
exactly. So you have to actually build a case switch statement that says go 14 octets in front because that was a type, that was TLV, blah, blah, blah. And now I go to the next TLV, and, I've got to actually work my way through the packet. It's a lot more complex to code. Nowadays, however, how many TLVs are there? I don't know. 25, 40. I don't actually know anymore. Whatever it is, it's not that simple anymore, honestly. Now OSPF implementations tend to be this, like the last one I seriously worked on other than FR routing, which I don't really work a lot with OSPF and FR routing for various reasons. But anyway, was a two-dimensional data structure. And what would happen is when you got a packet of this kind, it would walk down the data structure and across the data structure, depending on what had happened last. And it would have a pointer to the correct function to call to take the next step. And so it was like this really weird way, but it was like the simplest way to do it. I still think of OSPF as being, particularly OSPF v3, as being useful. I personally think that ISIS scales better, just my experience. It's a simpler protocol. I think it's simpler to troubleshoot. A lot of people think that OSPF is simpler to troubleshoot. I think ISIS is simpler to troubleshoot, honestly.
Why do you think it's simpler to troubleshoot? Is this because if you get into multi-area configurations, what's driving the simpler to troubleshoot?
I think that ISIS does a better job of separating flooding from shortest path tree from reachable destinations. Those are 3 distinct things in ISIS.
Basically the same.
Yeah, but they're all using IP addresses in OSPF. So when I look at my table, I don't know what's what. In ISIS, when I look at my table, if it's a net ID, it's a node. If it's an
Yep.
IP address, it's a destination. Like
Okay.
just
Okay.
mentally, like things just separate. Flooding
I
is
see
going
that. Yeah,
to,
it's a notation difference. It's
yeah,
how
yeah,
objects are represented in the database. Not that the databases are different because they're basically the same,
yes,
but how
correct.
they're represented in the names and the name fields and so on. Right. You end up
Yeah, it's just
with a
easier for me to
SysID and
see.
ISIS
Right.
and
Yeah, it's
yeah.
just easier for me to see. I'm not
Yeah.
saying it's better. I'm just saying when I look at a database, it's easier for me to understand and quickly in a troubleshooting situation figure out the difference between these things. I don't look at an IP address and go, oh, am I actually reaching the node, or is that an IP address that's a loopback because it's a node, or is that a reachable destination that somehow got trapped on some other? No, 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 no. It's a net ID, and I've lost the net ID. I've lost the node. I mean, there's no question about what the differential is there.
Actually, Jeff addresses some of that in the book related to OSPF, how he recommends you assign a router ID and stuff like that. It
Mm,
has less to do with IP addressing and more to do with name it something you can understand what it is when you look at the database. You're
exactly.
going to save yourself some sanity.
That's exactly right. Yeah, that's a huge deal, and a lot of people don't do that, which makes OSPF a lot harder to troubleshoot. So the other big difference is going to just be inefficiency of flooding. So OSPF is more efficient in simpler. This is kind of hard to, but to me, OSPF is more efficient in simpler networks, just with less stuff. ISIS, as you get more complex stuff, more externals of different kinds, et cetera, et cetera, et cetera, ISIS is actually a simpler flooding mechanism. And it's more efficient in some ways. So on a broadcast network, ISIS tends to be a little bit less efficient than OSPF because there's a difference between a DIS and a DR.
It
Okay.
unicast to everybody, if I remember, whereas designated router and OSPF is the guy who
Yeah. Yeah.
ships to
So,
everybody else.
so in ISIS, if you get 10 people, 10 routers or 10 intermediate systems on the same physical Ethernet segment or the same virtual Ethernet segment, and all 10 of them get an LSP, a route update, they're all going to flood,
Yeah.
right? It's just that the DIS makes sure that everybody got it. Now, in theory, the first one that floods, the DIS should act and nobody else should reflood it. That's a timing issue. It doesn't always work that way. It's just about timing. With OSPF, the first router on the segment that gets it only sends it to the DR and BDR, who then reflood it.
Yep.
So if you only have 3 routers on a segment with OSPF, ISIS is probably more efficient with 3 routers on the same segment. If you have 10 routers on the same segment, OSPF is probably more efficient.
Yeah, so I guess that ties into sort of a follow-up question then. There are design requirements where it could make a difference depending on, what you're designing for.
Yeah. It's kind of, I mean, it's kind of trivial. I mean, when you get to the point where you're worrying about whether you have 10 routers on a segment or 3 routers on a segment, I
Yeah.
don't know. But on the flip side, right? Just because of the way OSPF formats its packets, you really cannot do partial SPF. I mean, you can, but it's hard because of the types and because of the way it carries the data. So in ISIS, it's very, very simple to do a partial. OSPFs can only do part. Let me put it even a different way. ISIS, all routes are external. They're all external. Every
How it
IPv4
carries them.
vSORTS
Yeah.
route is an external. It just has either an internal metric or an external metric. But that has nothing to do with how the protocol treats the routes. They're all, you build a tree, you hang the routes off of the tree. In OSPF, I actually have a difference between internal and external routes that makes a difference in the way they're flooded. Not really the way they're flooded, but the way they're treated in the SPF algorithm when I run my SBT, which means internals, because they are what kind of integral to the tree itself, can't be partial. You can't, like if I have 5 routers in a row and the last router, and they're all internals in OSPF, and the last router loses a connected route, I have to run SPF over all 5 routers.
Mm-hmm.
In ISIS, regardless of whether it's internal or external, it doesn't matter. If the fifth router loses a single route, just the interface goes down. Nobody runs SPF. Nobody. Not even the router that originates the LSP.
So from an architectural perspective, if I'm trying to decide between these two protocols, we're talking about issues that mattered 20 years ago when I had very limited control plane CPU and I was very worried about this kind of efficiency. And I was thinking carefully about how big to scale an area, the number of routers because of the number of SPF calculations that might get triggered. But isn't that kind of moot today with modern CPUs? Do we care about any of this stuff?
Yeah, I don't know. I mean, I tend to prefer ISIS in larger, meshier networks and restrict OSPF to enterprise network cores or things like that.
Larger, meshier networks. Does
Like
that mean a service provider network?
Like data
Yeah.
centers and use anytime you do traffic engineering too, because ISIS, I mean, I don't know what OSPF scales to recently because I haven't worked on a large scale OSPF network that's like at the scale that I've worked on. But ISIS, I mean, I've actually pushed 120,000 routes into an ISIS flooding domain
Mhm.
with 2,000 routers. And like it
Yeah.
just converges. Like, okay, big fat hairy deal. It just converges. So ISIS flooding domains tend to, in my experience, and again, this may just be because I haven't worked with OSPF in these environments in a long time, you tend to be able to build larger flooding domains with ISIS than you do with OSPF. And that's partially because of the partials. There's other reasons that is. The way that it floods, you don't flood an entire LSA, you flood fragments of LSPs. It's a little more efficient in that realm. And the more you have point-to-point links, the happier ISIS is going to be. I mean, it's okay with large flat flooding domains or large flat broadcast domains, but ISIS was really originally designed for point-to-point links
So
and
then talk
all
to
the
me about
dissonance.
multi-area then. You know, if you're talking about an ISIS domain where you shoved 120,000 routes into it, 2,000 routers, was that broken up into areas or was that just
Nope.
one great big area?
One level two flooding domain.
Yeah.
And that's
Yeah.
a lot of times how people deploy now. They don't deploy flooding domains. It's just, you just build whatever you're going to build. Um, I mean, 90% of the time people over divide even the OSPF networks, in my opinion. You really want to divide flooding domains up based on administrative reasons, like I am trying to create a subset of the network here in which I can troubleshoot or manage things without impacting the rest of the network. For instance, if I'm in a hierarchical network and I want to be able to replace a particular campus network without messing with the rest of the network, okay, make it a separate flooding domain. Got it. Because that's a life cycle issue that you run into. If, however, you are breaking up your flooding domains just for processor and memory, 90% of the time you don't need to.
We
You
recorded a podcast a decade ago on exactly that topic, and
yeah,
everybody that was on there, I brought in guys from a variety of different network operating environments, and they all said, just it doesn't matter anymore. The
no,
CPUs can just
not really.
handle it, unless even if you've got a flappy route that's throwing a lot of
Yeah,
noise and triggering a lot of SPF calculations, it's fine. It can take it.
yeah. I would say you should monitor your SPF time. And if you see your SPF time jump consistently, then you need to go troubleshoot why that's happening. And it may be that you've added a lot to the network that's causing the SPF time to jump, in which case you may want to split that new part off as a flooding domain,
Yeah.
kind of a thing. But just to break up flooding domains just because you should. I once worked on a network where the person read the Cisco documentation, and it said to put the OSPF router in two flooding domains. And he took that to mean you could only put a single router in two flooding domains. So he designed his entire network around the routers being in area zero and one other flooding domain. And like, it was like this whole strange thing, like he had done with redistribution and stuff to make it where the router didn't have, yeah, it was very, very crazy. But
Get my head around that. Yeah. You mentioned the 2000 routers. The only time I worked on a network with that many routers in it was neither ISIS or OSPF. It was EIGRP, and we had stuck in active problems because it was a big gnarly WAN with lots of mesh going on, and had challenges there, and really needed to break that thing up into multiple domains. That's a story
Probably,
for a different day, but yeah.
probably would have been better off after you probably could have fixed a lot of it just by upgrading the code that does the SIA queries, active queries.
I don't remember what code family we were on at that point. It was either late 12 or early 15, something like that. And
Yeah,
I
we
can't say
ran,
how consistent we would have been across the routers either. So there
yeah,
may have been a bit of a mix.
we ran into situations where we actually threw hardware at that problem. We would actually add another layer of routers just to do aggregation and for no other reason.
Going back to your comment about the reason you do areas now would be administrative reasons. So say I'm in an enterprise and I'm going with OSPF and I don't need to do areas for reasons of controlling my flooding domains, but I want to for other reasons. Give us some reasons why in 2024, building a multi-area OSPF environment would be still valid.
I think the biggest reason is lifecycle management, personally. I think the biggest reason is I want to be able to pull this section of the network off, and I want to have minimal impact on the rest of the network when I do it. I want to take this entire data center fabric out of service. I'm going to make it a different flooding domain to do that. Now the reality is a lot of people never get to that point because they're going to connect a bunch of flooding domains together with BGP.
Yeah.
So that kind of like
Yes,
is
you end up with
the
standalone OSPF or
yes,
ISIS topologies that are
right,
interconnected with BGP at the edges.
right. Yeah, I've worked on a network once where people were arguing between OSPF and ISIS, and they brought this whole problem to me, and they were talking about all this, and I was like, well, how big is your flooding domain? How big is your network? And they were like, well, it's 5,000 routers, 10,000. I'm like, okay, so now, how are you actually connecting? They said, well, we're using BGP to connect everything together. And I'm like, well, how big's the flooding domain? How big's an individual flooding, your largest flooding domain? They said, oh, about 100 routers. And I'm like, well, doesn't really matter what you use.
Yeah, yeah, at that
Just
point,
use it,
right?
whatever. It's
Yeah.
just not that important at 100 routers. It comes down more to troubleshooting and skill sets and stuff like that.
Oh.
So then let's talk about BGP for just a minute before we entirely
The trash can
end
of the internet.
this discussion. Yes, yes, the trash can of routing protocols. Everything goes in there. BGP, of course, is become popular in data center topologies. It scales well. It's got a lot of policy capabilities. Many things you can do with it. When would I use BGP instead of OSPF or ISIS?
So the number one reason I hear people saying, well, number one and number two reasons I hear people saying they use BGP is number one is because everybody else does it.
That's a great
And
reason.
it is. It's an awesome reason. And all the validated designs use BGP. All of them. Yeah, okay, whatever. The second reason I always hear is because, and I find this rather hilarious, by the way, is because nobody in my operations center knows any routing protocol other than BGP. And I find that utterly hilarious because 10 years ago, 15 years ago, I would go out to customers. I worked on big tank networks and this, that, and the other. And I'd be like, your network is large enough that you really need to start breaking up your flooding domains in OSPF or your query domains in EIGRP and putting things back together with BGP. And they were like, oh, no, BGP is for service providers. It's too hard to configure. We can't do any of this stuff. So it's like totally reversed. All those people who didn't know anything, didn't know BGP 10 years ago, now only know BGP. I'm not sure how that happened.
I don't know.
Yeah, who's out there waving the BGP flag so hard?
It's just really funny. So I don't know. You can use BGP everywhere if you're okay with the convergence and stuff. I think we've gotten to the point where we're using it everywhere and we just keep stuffing stuff into it. And someday we're going to have a failure of massive proportion. I think we already have. I just don't think it's been reported this way, where the protocol is so complex and somebody turned one knob left when they should have turned it right because the knob was there and like, bam, everything just blew up. I think we're already having that happen. Just people, they're calling it automation mistakes or whatever, but you can automate whatever you want to, but if you automate, like, they used to have those airplanes that had the backward wings,
Yeah.
Uh-huh.
right? And they wouldn't fly if the electronic system fell apart because they were so unstable in flight
Mm.
that they would actually use electronics to micro adjust all the flaps and everything. Yeah,
Mm.
that's kind of what I feel like we are today. Like,
Yeah.
I kind of want my network to be able to coast when the engines go out. I don't know.
Glide into an easy landing, not just fall out of the sky.
It's kind
So,
of the thing.
given that, would you then advocate that folks, if they are designing a new network, think about OSPF or ISIS instead of BGP internally?
I don't know that I would necessarily say instead of, but in addition to.
Mhm.
Mm.
Depends on the scale of the network and what your purposes are, right?
Right, of
But like
course.
even for data center fabrics, I really prefer to have two routing protocols. I really prefer to have an underlay and an overlay. And this may just be old habit because back in the day when we built large scale transit networks, we never used a single protocol. Infrastructure routes were clearly separated from customer routes.
Uh,
You knew
uh-huh.
which was which. You knew what table to look in to get to which. All the policy was in one table. All the reachability for tunnel endpoints, head ends and tail ends was in another table. And that was just like such a clear separation of duty. It made it so much easier to troubleshoot. And nowadays we stick infrastructure and overlay routes in the same protocol. And like, it's just a big mess.
So, are there any other routing protocols in the modern era that are worth considering other than we've kind of talked about the classics here, OSPF, ISIS, and BGP, something like Babel or anything. What was the name of that thing? Rift? Was it Rift that Tony P was working on? I
Yeah,
forgot.
Rift, OpenR. So my impression of OpenR is basically OSPF using 0MQ or RabbitMQ as the flooding mechanism. That's pretty much what
Message
it is.
bus.
Yeah, message bus as a flooding mechanism instead of flooding through OSPF. That's cool. Whatever. Um, Rift is cool in large scale butterfly and clow fabrics. I don't know that anyone listening to this is going to be large enough to need to consider Rift. There was some stuff around auto EVPN with Rift that looked pretty cool. I think
Hmm.
only Juniper ever implemented it,
Huh.
as far as I know.
It was like something some
And
customer asked for, maybe.
yeah, it was kind of a cool thing that you could do too,
Hmm.
because Rift knows which it knows whether it's every router knows whether it's at T1, T2, or T3, or T0 to T1, T2. Basically, the router knows where it is in the fabric to some degree, and so you can do lots of cool things with that. Now, the original Open Fabric drafts had a way of doing that as well, which Rift kind of took over. But we pulled it out of the original Open Fabric drafts for a desktop flood because I don't know, it just feel to me a lot of the problem with this when you get too deep into auto configuration comes back to troubleshooting. If you're auto configuring everything, like if you're auto configuring your net IDs in ISIS, well then you don't know how to troubleshoot anything because you don't know what the network actually looks like. You're like looking at net IDs and going, what? Where is that? I don't know. It was auto generated. Who knows what that is, right? And so that's not very useful. It's like auto generating router IDs in OSPF, right? If every router auto generated its own router ID, you wouldn't know any of the router IDs. You wouldn't be able to read the database. You'd be completely lost all the time. So there's some degree of that that's kind of odd. But I don't know how popular Rift is now. I know we're still working on flooding optimization in ISIS, in the link state routing working group in the IETF. Just got a new version of the draft, and there have been some changes because there are some attempts to unify, or not necessarily unify, but make it where different ways of flooding optimization can interoperate in a rational way. So there's been some work going on there.
Did TLVs and OSPF ever take off? Because I know there were some standards around that, but it's not like you hear much
Yeah,
about that.
OSPF v3 has TLVs. Who has implemented it? I don't know. It's not implemented in FR routing, as far as I know.
Hmm.
But then again, the OSPF v3 implementation in FR routing is not a very, in my opinion, not a very good implementation of OSPF v3. It's a bit of a shortcut implementation, but I think it was a doctoral student or something that did it, and it was cool. I mean, it works for what it does, and this, that, and the other. Would I deploy it at scale in a production environment? I'm not really positive I would. The OSPF v2 version implementation is pretty good. The ISIS implementation in FR routing is good, but the OSPF v3 is a little, I don't know. It just feels weird to me the way it was done. So.
Well, Russ,
Babel,
I think
Babel is only useful for one thing.
Yeah.
Mobile networks, pretty much. I mean, I know that I saw a blog post the other day that said use Babel to preserve IPv4 addresses, which was really interesting use of Babel. But I don't know of many uses of Babel that aren't ad hoc networks of some kind. So sorry, continue, Ethan.
No, that's okay. I was gonna wrap here for this first episode of Q&A with Russ. We got through 2 questions, each with about 20-minute long answers and discussion. So that was good. I thought that's maybe one more than I thought we were going to get. I wasn't sure. So
how many more questions do you have for the next part of this?
Well, we're gonna do 2 more in another episode, Russ, is what's gonna happen. So we're gonna wrap this one, and then we're gonna have you back, and listeners, you can stay tuned for that. We're gonna have Russ back to discuss some more things about VXLAN EVPN and networking data models, and what would a Russ White designed certification for network automation look like? That's going to be in our next episode with Russ. So Russ, for now, how can people find you on the internet? Because you are everywhere.
No, I'm not everywhere. I'm in rule11.tech. That's the best place to find me.
Rule11.tech. Indeed, that is the best place to find Russ. And thanks to you out there for listening all the way to the end. We went hard on the nerd meter this week, that is for sure. If you would like to get stuck into one of Russ's books, courses, podcasts, or blogs, again, check out that site of his, rule11.tech. He's got everything there linked for you, including the book that Russ and I wrote together, Computer Networking Problems and Solutions. Here at Packet Pushers, we offer lots of other resources to you at packetpushers.net, including a Slack group, industry blogs, newsletters, and several more podcasts for your professional career development. Take a minute to click around and you will find things like a list of free open source software for networkers and a way to contact us with your follow-up. You can tell us exactly what you thought of this episode, send us questions, or relay anything you'd like to follow up with us about at packetpushers.net/FU. Vendor friends, we have lots of opportunities for you to engage with us here. Send us your nerds and let's talk to them about the cool thing you're doing. Thousands of engineers who specify what tech their companies buy will be listening. Find out more at packetpushers.net/sponsors. We have openings on our network as we've introduced new channels for 2024, including the Network Automation Nerds podcast and the Packet Protector podcast covering cybersecurity. Last but not least, remember that too much networking would never be enough.